It is time for another Lagrangian mechanics problem, finding the equation of the force of constraint. So, there's this problem, and I'll show you to you in just a second. So there's this famous problem of a sphere with a block of ice on the top, and then you push it, and then you want to know what angle does the block leave the surface of the sphere if there's no friction. And it turns out, I think theta is cosine inverse of 2/3. I actually have a video on this. Let me just switch to the video. Let's see. Here's my YouTube video of that solution. I do it two ways. I do it with a trick, and then I do it numerically. But let's just go. I'll link that down below. And it's an okay problem. But then I thought to myself, what if it was on a parabola? Would it leave the surface if it's sliding down a parabola? Or as some say, parabola. I like to say that. And I don't know. I mean, you could have a really flat parabola. You could have a really skinny parabola. And then I was thinking, because if you have a projectile motion, the trajectory is a parabola. It'd be a different parabola, though. And then I was like, well, if it's really steep, it's going to fall off. But then I thought, well, if it's really steep, if it's like this, then it's not going to have enough time to pick up you have to have a horizontal velocity in order to come down. So I don't know. Maybe there's no time that it ever leaves contact. But one way to do it is to do this problem. So we're going to do this problem. Yeah, that's what we're going to do. So here's the equation of my parabola. Y is negative ax squared. So a is a parameter that tells you how stretchy this is, I guess you could say. So this is a Lagrange multipliers equation of forces of constraint problem. So we're going to define the Lagrangian, kinetic energy minus potential. We're going to define the equation of constraint, x, some function of x and y is equal to 0, which is going to be from this. And then we're going to write down the modified Euler-Lagrange equation, which says the partial of L with respect to x plus lambda, which is the constraint parameter, partial of f with respect to x is the time derivative of the partial of L with respect to x dot, and do the same thing for y. And then the force of constraint, we're going to have an x and a y force of constraint. The x constraint is this lambda partial with respect to x. Y is that. Okay. So let's start off with this. I'm going to write this function. I want this. This is my relationship between x and y, but I want it in terms s equal to 0. So that's pretty easy. I can say f of x, y is just y plus a x squared equals 0. So there's my function. Now I need to write down my kinetic energy term. Is this marker going bad? That looks okay. In this case, I'm not going to use some angle theta to describe the location. This is because it doesn't work that way. It'd be better to just use Cartesian coordinates to begin with. So if I use x and y, which I can do, then I'm going to say t is just 1/2 m x dot squared plus y dot squared. Now, if I was doing this as a 1 degree of freedom problem, which I did before, except it was up, then I could eliminate the y dot by taking the derivative of this and getting it all in terms of x dot. But in order to define the equation of constraint, I need to under-constrain it. I need 2 degrees of freedom, even though it's really just 1. The potential energy U is going to be mgy. So that means my Lagrangian is 1/2 m x dot squared plus y dot squared minus mgy. Okay, let's just jump right to it. Let's start with the x. Okay, let me rewrite my functions. So I have f of xy is equal to y plus a x squared equals 0. And then L is 1/2 m x dot squared plus y dot, that's a squared, dot squared minus mgy. So the first thing I'm going to do is I'm going to use my Lagrange, and I need to take all my parts. So let's do the partial of L with respect to x. And that is going to be, where is the x in there? There is none. 0. Now I need to do the partial of f with respect to x. And you see here I do have an x. So I'm going to use the power rule, and this is going to be 2ax. Now I'm going to take the partial of L with respect to x dot. There's only one, so I have 1/2 m x dot squared. Use the power rule, and I get m x dot. And then the derivative of that with respect to time, the partial of L with respect to x dot, is just going to be mx double dot, right? Because mass doesn't change with time. I take the derivative of x dot with respect to time, and I get x double dot. So if I put this all together, I get 0 plus lambda 2ax. This is the partial of L with respect to x plus lambda times this equals this. And there I have a useful equation. Okay. Now let's do the same thing for y. The partial of L with respect to y is going to be equal to this, negative mg. The partial of f with respect to y is 1. The partial of L with respect to y dot is just going to be my dot. And then the derivative of that with the partial of L with respect to y dot is my double dot. So if I put this all together, I get negative mg plus lambda equals my double dot. That looks nice, huh? Okay, so I actually have 3 things that I don't know, right? I have 3 equations, and I'm trying to find, I really need to do 2 things. I want to get like x double dot as a function so I can model this, and then I want to find lambda. Let's just go ahead right up here. If I have x double dot, I can find lambda. So this just says lambda is going to be mx double dot over 2ax. So that's kind of useful. So if I know x and x double dot as some function of time, then I can get lambda, and then I can get both the constraint forces. Okay, that is right? Yep. Okay, that's right. So I want to eliminate these x dots and y dots, and I do have a relationship for that. Let's just take this and say y is negative ax squared. Now if I take the derivative of both sides, I get y dot equals negative 2ax x dot, right? Because if I take the derivative of this side with respect to time, then I have the 2 comes down front, but then I have to take the derivative of x also, so I get x dot. Now I want, see if I do this again, I can get a y double dot in terms of x double dot. So let's take the derivative again, y double dot. Now I'm going to get 2 terms. The first one is going to be negative 2a x dot, right? Because I take the derivative of this term with respect to time is x dot. And yes, that's x dot squared. And now I need to take the derivative of that, and I get minus 2ax x double dot. And so this is minus 2a x dot squared minus 2a x double dot. Now I can plug that in over here and solve for things that I want to solve for. So let's solve this for, let's just put in my y. Let me rewrite, I'm going to start a new piece of paper. So let me put all my things, I'm going to put this equation, lambda 2ax equals mx double dot. I'll put it over here, lambda equals mx double dot over 2ax. And then I have this equation, negative mg plus lambda equals my double dot. I'm thinking out loud here. And then I have this y double dot is negative 2a x dot squared minus 2a x double dot. Okay, so what I want to do, I just thought about it. What did I do? Let's see. What do I want to do? I want to solve. Let's get rid of the lambda in these 2 terms. I have 2 lambdas. So let's solve this for lambda. Plug it in up here, and then plug in y, and I'll get an equation with just x's in there. Okay, so lambda is going to be my double dot plus mg. If I substitute that in up here, I get my double dot plus mg times 2ax equals mx double dot. And let's go ahead and that's a y double dot. Let's multiply this out. I get 2ax m y double dot plus 2ax mg equals mx double dot. Now I'm going to substitute in my expression for y double dot in here, and I'm going to just get x stuff. So if I do that, I get 2ax m negative 2a x dot squared minus 2a x double dot. That's that term. Then I have this one plus 2ax mg equals mx double dot. Now I'm going to multiply this out. I get negative 4a squared m x dot squared. And then the other term is going to be minus 4a squared x squared mx double dot. And then I have this plus 2a x mg mx double dot. The mass cancels. Nice. Okay. Now, I want to get x double dot, so I'm going to add this to both sides. So I get negative 4a squared x dot squared plus 2axg equals x double dot times 1 plus 4a squared x squared. I added that to both sides. I factored out the x double dot. One line with 2 steps, because that's how I roll. Now I can just divide both sides by this, and it looks complicated, but I don't care, right? X double dot is equal to negative 4a squared x dot squared plus 2axg, all of that over 1 plus 4a squared x squared. Okay, so that is important. So once I have x double dot, and then I have up here, remember, lambda. And so if I find this as a bunch of times, then I can find that at a bunch of times. You see how that works? Okay, so what do we do next? How do I solve this differential equation? The answer is I don't want to. I mean, maybe there is a solution, but let me write this equation. And my 2 things are important. Lambda mx double dot over 2ax and x double dot negative 4a squared x dot squared plus 2ax g. You know, if you're working on problems like this and you don't mind, it probably does help to say things out loud. I mean, that's just me. Maybe it doesn't help you. It helps me. I do make mistakes. We all make mistakes. Everyone makes mistakes. Okay. So now the key is to do this as a numerical calculation. So let's say a small time interval of 0.01 seconds. During that time interval, I can assume that x double dot is constant. It does change. It has a velocity and a position term in there. A position. But if I assume it's constant, then I can write x double dot is equal to delta x dot over delta t, or x2 dot minus x1 dot over delta t. So this is the velocity at the beginning of the time interval. This is the velocity at the end of the time interval. And this is like the finite derivative, a difference really. Assuming this is constant, then that would be true, right? Instead of dx dt is delta x dt. I can take this and solve for x2 dot. I get x2 dot is x1 dot plus x double dot delta t. Now I can assume x2 dot's constant. And if I do that, I know it's stupid to do that, but I'm going to do it anyway. I can say that's the change in x with respect to time, or x2 minus x1 over delta t. And I solve this for x2. x2 is x1 plus x2 dot delta t. So that's important. This is important. And this is important. So here's our plan. Calculate x double dot. I need to know initial conditions. I need to know the initial x double dot, the initial, I don't need the x double dot. I need initial x1 dot. I need initial x. Okay, and then I can calculate x double dot and use that to find the velocity at the end of the time interval, the position at the end of the time interval, and then go back up here and do it for the next time interval. And I can do this as long as I want. I can do this all day, as Captain America would say. And then I can actually, if I want to plot the motion of this, I can do that. I can plot the motion of this. Right now I'm trying to think if I want to do this as a visual or just a graph, and I feel like I might just want to do it as a graph. But if I want to plot the trajectory of this, which is what I'm going to do, if I want to plot the trajectory, once I know x, I can find y, right? Because y is just negative ax squared. So I can find that. And I think that's all I need, because this doesn't have y double dot in there. I don't think I need that. Okay. Decisions. I'm going to do a graph. I just decided in my head. I'm going to do this graphically. So what I'm going to do is, but then how do I know if it leaves the surface? Let's go ahead and address that question. Because FCX, the constraint force in the x direction is going to be lambda times the partial of f with respect to x. And so I know that's lambda. I already took the partial of f with respect to x way back here. To ax. So this is going to be equal to this mx double dot over 2ax times 2ax. That's strange. Let's see. That doesn't seem like that would be the case. Yeah, okay. That's fine. That's what it is. And then the y component, fcy, is just going to be lambda, because the partial of f with respect to y is 1. So if this is a vector, right, I have the x and the y components. If the magnitude of that goes to 0, then it loses contact. There's no constraint between the bead and the wire, and it loses contact. And you'll notice here that one of the things that they both have in common is lambda. I think I can just say, when does lambda go to 0? So I'm going to plot lambda as a function of x and see what happens. That's what I'm going to do. So the first thing I'm going to plot x as a function of y, a trajectory, and then I'll find that graph right there. So let's jump to it. I do need some initial conditions. Let's pick a mass of 0.1. G is 9.8. The initial x1 is going to be 0.01. It can't be 0, or you would get, if I put in x equals 0, 0, 0 over 1, x double dot 0, so it wouldn't move, right, because it's flat up there. And then x1 dot is 0. Oh, and a, let's just do a as 1. We can change that. Okay, jumping over to Python. Okay, let's do this. I'm gonna make my graph. I already told you I'm gonna make 2 graphs actually. I'm gonna make 2 graphs. So let's just do the first graph. Is this big enough? Make it bigger. Bigger, that's good. G1 equals graph, title equals parabolic bead. I like that. Y title, X title is, I'm gonna make a trajectory. So this is gonna be X in meters, and then the Y title is Y in meters. And then let's make it a good size. Width equals 400, height equals 200. And then I need something to plot. F1 equals G curve, color equals color dot blue. Okay, next thing I want to do is declare all my initial conditions. So A equals 1, G is 9.8. I've already assumed G, I'm using the magnitude of G in my calculations. X equals 0.01, X dot is 0. T equals 0, dt equals 0.01. Let's see, did I miss something? Oh, M. Let's put it up here. It looks better. M equals 0.1. And that's because you could pick any value for M, obviously. But if I'm actually plotting lambda does have an M in there. Okay, let's run it for 1 second. I'm just picking 1 second. Okay, so while this is not big enough. I like big. While t is less than 1, up here I'm going to do this. Dot equals true. So dot equals true when I make that graph. The point that I'm plotting is going to have a bigger dot so we can actually animate the whole graph. It's going to be awesome. Okay, so but that means I need to add rate 100. So I want to say don't do more than 100 calculations per second. So it'll take a second to run this whole thing. Okay, so the number one thing is to first calculate x double dot. So I'm going to say x d dot is double dot, is equal to, now I have my equation right here. I'm going to type my equation, -4 times a squared times x dot squared. Right, that's what I had. Plus 2 times a times x times g divided by 1 plus 4 times a squared times x squared. Okay, so that's x double dot. Now that I have x double dot, I can calculate x dot. X dot equals x dot plus x double dot times dt. And remember, this is a make equal to true equation, not an algebraic equation. So it's not, these variables they're not variables that cancel. Now I can calculate x. X equals x plus x dot times dt. Now I can calculate y. Y equals negative a times x squared. Now I can plot it. So let's plot it. F1 dot plot. I want to plot x versus y. And now I'm going to update the time. T equals t plus dt. I don't know if that's going to run. But look at that. That's not even that bad of a code. So it's kind of nice. Let's run this. Looks parabolic. It took 1 second. Okay, so there you go. Nothing fancy, right? It doesn't really tell me anything other than, yes, it did do a parabola. But the bead stayed on there because I never told it could leave. I mean, x double dot, assuming the bead stays on there. There is a force of constraint, but it could pull or push or do anything. And the thing is, if it has to pull to be on there, then it could leave the parabola. So let's plot lambda as a function of x. That's what I'm going to do. So let's make a second graph, G2 equals graph. And I'm going to put title equals constraint parameter. And then let's do x title equals, that's not title. Title equals x. I could plot it versus time or anything, but I'm doing it versus x. Y title equals lambda. Lambda. And the units would be, I think it's in newtons, but I'm going to leave that off. And let's put width 400, height 200. Same thing. Now, okay, so if you have more than one graph in Python, you actually can say which function goes with which graph. But if you do it in order, I think it works fine too. So I'm going to say F2 is gcurve, color equals color.red. Let's just make it different. So that one will go with G2 just because it's below that. I think. Okay. So down here, I do want to calculate lambda. So lambda is just going to be equal to, looking at my equation, lambda is m times x double dot divided by 2 times a times x. Now I'm going to plot that. So f1 dot plot x lamb. You can't say lambda. I think lambda is a reserved word in Python. So you can't, I'm calling it lamb. It's what lambda's friends call it. It's abbreviation for lambda, lamb. I don't know if this is going to work. Let's run it. What the heck happened there? Oh, you know what? I know what happened. I said f1 dot plot. Okay, so what do we see here? This looks like it's working. I want to know if lambda gets to 0, and it is getting small, but it didn't get to 0. So maybe I need to run it for a longer time. So let's do that. It's easy to do. 2 seconds. Run it again. I'm looking at this. Oh, look at that. It got to 0, but it didn't go negative. And I think if I kept running this further, it would just stay in a parabolic trajectory, right? Because a parabolic trajectory, this is in space, you can have any trajectory depending on your initial velocity. So I think it's just has merged into the free fall parabolic trajectory. So technically it does lose contact in this case. It just doesn't leave. And there's just no force between that. That's kind of interesting. And I know someone that's going to think that's really interesting. You know who you are, and you're going to make a a mathematical version of this, and you're going to change it up so it's spinning or something like that. And I love that. Okay. But let's see. What if I make it a broader parabola? Does it still do this? So if I go up here and let's just change A to 1.5 and run it. Now the graph doesn't look any different because it's rescaling automatically. But the same thing happens. It got down to, and this is again at x equals 1. I wonder if that's always going to be the case. Around x equals 1. Let's see. Okay, now let's try a skinnier parabola. Let's try just 0.5. I'm looking at this. Okay, so it did change. And it didn't get to 0, right? But I think that it would get to 0. So let's run a broader parabola. Let's go to 2.5, and let's run this for 4 seconds, just to see if we can get this to work. If I was right about it not getting negative. Because you'd have to have, now, do you have to have a negative lambda? No, not actually. I mean, you want the force to be in the kind of negative x component. I think that have to be because you're almost completely vertical, but you're multiplying the x component by, what is that? Lambda times 2ax, and x is positive, so it's not going to do that. I think it's not going to lose contact. That's my claim. I'm pretty happy with this. I could be wrong. Tell me I'm wrong. But okay, so I'm going to link down below my playlist for Lagrangian mechanics from second semester with other force of constraint problems. I'm going to link this code down below. And I'm going to link, put a link to my previous video on the bead on the bowl of ice down below also. Okay, that was fun. I'll talk to you later.